All right, so today I'm going to be talking to you about dynamic instrumentation. So dynamic instrumentation is really any technique that allows you to attach to running processes and add instrumentation logic to them live and collect information about the execution of the program so that you can debug issues or just better understand how your programs are running. So these are the technologies I'm going to be diving into. So we have Delve, which is the Go debugger, Ptrace, uprobes, BPF, and Frieda. Just to begin, I kind of want to take a step back and look at the different classifications of instrumentation in case folks aren't familiar. So I like to categorize instrumentation to three different tiers. So the first is static instrumentation that is always on. So this is instrumentation you add to your program in advance, like you add to the source code. It gets baked into your Go binaries and it's always on, so it's always collecting data. As a result, you can't really instrument every aspect of your system because that would just incur too high of a performance penalty. So you kind of have to be selective where you add this instrumentation. A layer below that is static instrumentation that you can add to your programs in advance, but it requires some form of activation. So a good example of this is like level logging. So if you ever use a level logger, some of them can dynamically reconfigure to have more granular logs at runtime. So that's kind of an example of being able to dynamically reconfigure some static instrumentation. pprof, if you're familiar with pprof, there's like a CPU profiler. That's a good example. It's baked into your program, and when you activate it, you can take the performance penalty to capture a CPU profile. So that's like a good example of static instrumentation that requires some form of activation. And then finally, what we're going to be talking about today is dynamic instrumentation. So this is instrumentation that you don't add to your program in advance. You just take an arbitrary program, you come up to it, and you add the instrumentation live. So some good examples of that are debuggers, tracers, and technologies like uprobes and BPF. And the advantage of dynamic instrumentation, there is still a performance penalty to them, but they give you the maximum amount of coverage. So if you have a bug in your system, you don't have to add instrumentation, recompile, redeploy, wait until the bug reproduces, and then go through that very long feedback cycle. You can just go and attach directly to the process. So it allows you to instrument really any part of your system live. So yeah, I was diving through the mailing lists and I kind of found this post that Rob Pike was commenting on. And he was talking about dynamic instrumentation. He said, I want a toolkit that can examine running programs and answer arbitrary questions about them, questions that I don't know until the problem arises. And that's really important because a lot of times when you're debugging an issue, like you want to be able to ask a question and you need to add specific instrumentation in order to answer that question. And you don't know what types of questions you want to ask until the problems arise. So you can't really bake that into your binary up front. So yeah, he said, I like to not require compile time changes, and I like to come to any arbitrary program while it's running. I want a programming interface which I can build whatever is needed, either generally useful tools or ad hoc probes, and the programming language I want to use for this is Go, obviously. So unfortunately, what Rob Pike wants doesn't really exist yet, but there's been a lot of developments in the Linux kernel and different tooling that provide a good deal of capability. So we're going to dive into some of those techniques now. So the first is Ptrace and debuggers. So debuggers are incredibly powerful tools, as I'm sure everyone's aware. And debuggers use this system call called Ptrace, short for process trace, in order to do a lot of the functionality of the debugger. And Ptrace gives you these five main features. It allows a process to suspend and continue the execution of another process. It allows that process, once it has suspended the process that it's tracing, it allows it to single-step instructions. It allows it to read and write to the memory and registers of that process, and it also allows it to intercept signals for that process. So using those five features, we can implement something like breakpoints. So something you might be familiar with from a normal debugger. So let's kind of look at how that happens here. So on the left-hand side, we just have user space. So it's our Go process just running as normal. And then we have Delve, which is also just a Go program running in user space. On the right-hand side, we have the kernel. So this is where the ptrace logic is implemented. And then also any interrupt handlers, the kernel registers with the CPU will be in the kernel address space. So let's just kind of zoom in on our Go process here. And on the left-hand side, I kind of zoomed in. Each one of these bytes is an individual byte of memory. And the top three here, B80100, is just a instruction. And then B800 down here is another instruction. So we're going to actually focus in on this second instruction here is B800. And that's going to be the instruction we want to set our breakpoint at. So this is just kind of how the program runs as normally. The arrow represents the instruction pointer, just kind of executing instructions. So Delve will use Ptrace to set a breakpoint. So call in the Ptrace, and the first thing it does is it copies the first byte of the instruction that we're going to be instrumenting here, copies that into its own memory. It'll then write into memory this value CC, which is our breakpoint. And that's just a single byte instruction that will trigger a trap for us. So when that occurs, execution is handed over to the kernel, and the kernel will then send a signal to the process, and that will get intercepted by Delve. Delve can then take an arbitrary amount of time to run to do whatever debugging is needed. So typically you'll be poking around, looking at memory, looking at registers, dumping stacks, stuff like that. And then once you're done debugging, the Delve will then call back into Ptrace, and it does this kind of like weird dance here where it will take the original byte, write it back into the memory, reset the instruction pointer back before the original breakpoint. It'll then single step that instruction. It'll then put the breakpoint back, and then it'll continue execution from there. So there's a lot of machinery involved into maintaining these breakpoints in memory. So this is great. We can intercept our code where we want to be able to intercept it, but the major problem with this is suspended execution. So back before, when Delve's kind of just spinning there, that can take an arbitrary amount of time, and while it's running, your process is not running. So if you're using these techniques to instrument live systems where performance is critical, this kind of isn't really viable. So we can minimize the amount of time that we're spending in the debugger by automating our interactions with it. And Delve exposes this a really awesome JSON RPC API that we can use. So this is a technique I've used a lot. It's kind of like my first go-to thing for dynamic instrumentation is I try to instrument using this technique. So let's kind of see how that works. So we have now a third process in the mix here. I call it a controller, and it'll just talk over that JSON RPC API with Delve and automate everything with it. So I'm going to show kind of an example program here. That's going to be our Go process, and it's pretty straightforward. It's just a counter. So we have a global counter. We have a function called doWork that will increment that counter. And then we have a main that just loops forever calling that doWork. So pretty straightforward. When we run that, it just has no outputs. It just says, I'm a black box. And so we have no way of kind of finding out what the value of that counter is from the outside. So let's go ahead and implement the controller. So this is the process that's going to use the Delve API to automate Delve. So this is what that looks like. So we just have a exec command, tell Delve to attach to the PID of our process. We run it in headless mode, specify API version, the adder to listen on, and then we just start up Delve. And then there's a little helper function I have here to kind of pull on that adder to make sure that it's actually accepting connections. Not really that important, but you want to make sure Delve is actually listening before you connect to it. We can then use the Delve RPC client library to interact with Delve. And this is a really nice client library. So we just create a client. We tell the client to continue. So all the time from when Delve attaches to this point where we continue, the process has been suspended. So we want to be able to continue it as soon as possible. That way it goes back to doing work. And then we just defer a function to halt the child process and then detach from it. And then, so one of the things that you can do in the Delve API is to resolve addresses in your process that you're instrumenting. So in this case, we just call find location, and the important bit here is the symbol name that we give find location. So it's main.doWork. So a little bit of background about like symbol names in Go. So if you just obj dump like a binary in Go, The addresses are on the left-hand side here, and then you can see the symbol names on the right. So you can see like most of them are like fully qualified with the package name and type information and everything. That's how like it is normally for normal symbols, but since main is special, there's only one main package. They kind of just have the main prefix for main symbols. So we just use that here, main.doWork, and then that'll give us back the address of where that function is located in memory. We can then create a breakpoint. We just give it a name, the address that we read, and then this third section here is kind of optional, but it's really useful. It's a slice of strings that is any expression that gets evaluated in the context of where that breakpoint occurred. So in this case, we want to be able to read that counter value, so we just say counter. We then go into this infinite loop where we halt the child process, we create our breakpoint. We then call continue, which will continue the process until the breakpoint is hit. Continue returns a channel that blocks until that breakpoint is hit. And then once that unblocks, we read this value. It's called the debugger state, and that has the values that we want, the value of the counter. We can then clear the breakpoints by name and then continue. And what that does is makes it to where any future invocations of do work don't get impeded by the breakpoint. Once that's cleared, we can then read the value from the debugger state and report it, just a string, and then sleep every second. So every second we wake up, halt the process, create the breakpoint, continue till the breakpoint is hit, and then once it's hit, clear the breakpoint, continue, and then report the value. So let's see that running. So on the left-hand side here, I have the counter running in a report mode. So this is just kind of reporting its states for us so we can compare the performance. And then we add our instrumentation, and you can see there's very little performance overhead in doing this. There's a little bit of a dip. You can kind of notice it went from 174 to 173 million operations a second. That was just the time it took Delve to attach and for us to continue Delve. So what happens if we want to intercept every execution of do work? So in this previous example, we were intercepting once a second. So if we want to intercept every single invocation, we can do that. This is just a program that does that. It just spins up two different Go routines, one to report the counter value to the user, and then the main Go routine, we create our breakpoint, and we basically just don't clear it. We just keep it in memory and keep on reading off these channels as they get hit, and storing that value so that the other Go routine can report it. So when we run that, again, we left-hand side just reporting the counter as normal, and then we add our instrumentation, and that has a significant performance impact. So we went from hundreds of millions of operations a second down to hundreds of operations a second. So this has a lot of overhead. So why are high-frequency breakpoints so bad? Well, there's a lot of I/O to transfer state between the controller and Delve. It's talking this JSON RPC. You have to like marshal messages and do I/O. A lot of context switches there. There's context switching just in the machinery of Ptrace in order to intercept these instructions. So that has a lot of overhead. Additionally, accessing memory using Ptrace, the API kind of it's like really slow. It can take up to like 100 times slower than normal memory access. So that's not ideal. So can we do better? So what if we could take like all this logic that we have in user space, the controller and Delve and everything, and kind of just like do away with that and move that all into the kernel? So we're just jumping into the kernel when instruction gets hit, doing the instrumentation in the kernel, and then yielding back to the Go process. So this is something you can do with uprobes and BPF. So uprobes are user space probes. It's a feature of the Linux kernel. And they allow you to trace any instruction in user space with a lot less overhead than the techniques that we've been demonstrating. So let's look at how like uprobes kind of operate here. So we have our Go process running as normal. We go to set the breakpoints, and in this case, the kernel will copy the entire instruction that it's modifying into kernel memory in a place called the single step out of line buffer. It'll then take that CC value, the breakpoint value, and write that into the process memory. And now when that trap instruction, when the breakpoint gets hit, the uprobe handler will get invoked. And then after the handler is run, the instruction that it copied into kernel memory will get single step directly from kernel memory. And then the kernel will then update the instruction pointer for the process to point to after that instruction, and then it'll resume from there. So it's a little bit more optimal than what Ptrace is doing. So you might be wondering, how do you write these uprobe handlers? So you could write a kernel module, but naturally, I imagine most people don't want to do that. It's not really the safest option, and it's kind of complicated. So we can actually use BPF to write one of these uprobe handlers, and there's a lot of tooling around doing this. So just a really quick intro to BPF. There was a talk yesterday about BPF, but in case you didn't attend that talk, BPF is an instruction set that allows you to build programs and inject them into the Linux kernel. The kernel will validate those programs to make sure that they're safe, and then it'll compile them so that they're fast. And you can attach various events to these BPF programs, and one of the event sources is our uprobes. So in order to compile these BPF programs, we're going to use a technology called BCC, the BPF compiler collection. And BCC is just a compiler for BPF programs that you write in C. And it assists you with interacting with the BPF programs once they're loaded into the kernel. And it's implemented as a shared object, libbcc.so. So let's see that Go process running again. And then we're going to add our instrumentation using BCC. So BCC compiles and injects the BPF program. The BCC then creates the uprobe for us and attaches that to the BPF program. So similar to like what we saw before with the uprobes, just kind of hits at breakpoints. The uprobe handler takes over. This time it's implemented in BPF, so we have complete control over it. And the rest of the kind of uprobes machinery happens. So one key feature of BPF is the capability of storing values in kernel memory and then asynchronously sharing them with user space. And the advantage of this is that you can instrument a high frequency of events and do some type of aggregation in kernel memory and not be impeded by communicating those values out to user space. So that hot path is unimpeded. So at some later time, the BCC program will kind of read that value from the kernel memory. So that's BCC. BPF Trace is like a new tool. It's developed maybe about a year ago. And it allows you to write these BPF programs in a really nice DSL. It's kind of awk inspired. So let's see an example of using BPF Trace to do that. So all that stuff with BPF can be kind of condensed down into these few lines here. So we just say, I want a uprobe. I'm going to attach the uprobe to this binary. So you give the full path to the binary. You give it the symbol name. And then the body of this kind of function here is kind of what runs inside the kernel as BPF code. So it takes the uaddr of main.counter and just dereference that and stores this into the @ symbol. And @ symbol in BPF Trace is just a default map, which will allow us to share that value with user space asynchronously. And then the bottom code here kind of runs in user space. It just every second it fires and it prints out that value and does a little computation to compute the rate. So let's see that running. So we add our instrumentation this time, and instead of hundreds of operations a second, we got hundreds of thousands. So a couple orders of magnitude better, but still there's performance overhead in doing this type of work. So it would be a lot better if we could write these programs in Go. So is such a thing even possible? Yes, it is. So there's a tool called GoBPF, and basically it's the bindings for libbcc for Go. So you can write some of these programs in Go. So let's see an example of using GoBPF. So the BPF part of the GoBPF program, you still have to write in C, which is unfortunate, but it's the current state of the art. So you just have a string in your Go program, and then this will contain all the C source code. And I'll just go through this really fast. So just a high level, we declare kind of like a global value here, an array of one single uint64, and that's where we're going to store our counter value. We then declare a function that's going to handle the events, the uprobe events. We then need to find a pointer to user space memory where the counter is located at, and we don't know this when we write the source code here, so I just did %d so that we can template that out at a later time. We then need to find the pointer in kernel memory where the value should be stored, and then we just copy from user space to kernel space. And then in order to resolve that symbol name, we can use Go here. So I just wrote this really easy like lookup sim helper function, and it uses a standard library to kind of range over the symbols and find the relevant symbol. So this is kind of the power of Go BPF, is that you get to use Go to automate these programs. This is just some wiring to kind of wire up the uprobe so that everything kind of works similar to what we saw before. And then this is that infinite loop where we're going through and just reading from kernel memory and reporting that to the user. So let's see that running here. And you can see it has similar performance overhead to the previous example with BPF Trace. They use very similar technologies, so it's reasonable that it has similar performance. So one other tool I kind of wanted to go into is a tool that uses a technique for doing user space only instrumentation. So what if we could just like not pay the performance penalty of doing a context switch with the kernel and just have the process instrument itself? There's a way that we can dynamically load our instrumentation and just have it all reside in user space. So there's a few options for doing this type of instrumentation, but the one that I like is this tool called Frieda, and it basically injects the V8 runtime into your Go process and then sets up a communications channel with the runtime. And you're then allowed to send little JavaScript programs into your process that you can then instrument your code with. So this is kind of an example of a program that does that. So this is so there's different bindings for Frieda. There's a Python one, a JavaScript one. There's no Go binding. So in this case, I'm just going to write it in Python. And we just have our counter up at the top. So this is living in the tracer's user space memory. And we just have a function on message that is going to report that counter. So every time it receives a message, it's going to store that in the global and then report it to the user. And then our main, we just tell Frieda to attach to the process that we're interested in. We create the script, which will inject it into the process. And then we wire up this handler and just tell it to load. This is the actual script that it's injecting. So this is the JavaScript bit that I mentioned. And this is pretty straightforward. There's just a set interval. So every second, it's going to send the current value of the counter out to the process that it's communicating with. And we just resolve some symbol names here into pointers. And then the important bit is the bottom part here where we tell Frieda to attach to the specific do work adder, and whenever that do work function is entered, on enter it'll run this JavaScript function which will read from the counter's address and store it in JavaScript memory. So when we run this, it has a little bit more performance overhead in the example that I'm demonstrating here because memory access in Frieda is kind of slow. So it actually has a little bit less performance than what BPF Trace and Go BPF can provide. But I benchmarked it on a few other tests, and you can get up to you can get up to several million operations a second using this technique. So some other advantages is you don't have to write any C, you just write JavaScript. And it's cross-platform, so you can do this type of instrumentation on the Mac, on Linux, on mobile, iOS, Android, whatever. So yeah, these tools are a lot more powerful than what I'm demonstrating today. These are very straightforward test programs. But I kind of wanted to demonstrate a little bit more of the power of these tools. So last night I wrote this program. So again, we have our counter on the left-hand side. And on the right-hand side, I wrote this mutate program that allows me to send any numeric value over to the process and actually write into the process memory. So you can see here I'm just sending some numeric values, like negative values, and it adjusts the counter just live here. So basically, it's sending that message over the communication channel, and there's some JavaScript on the other end that just writes the value. Some other things that you can kind of do with these tools, so BPF, GoBPF and BPF Trace have really good support for computing latencies. So this demonstration here, kind of on the left-hand side, I'm just hitting Google with a bunch of different requests, and then I'm computing the latencies of each one of those requests. And when I hit Control C, you can just see like it prints out a distribution of the latencies of each of those invocations. So it does some pretty cool stuff. So yeah, we have 4 really great options for doing this type of instrumentation: Delve, BPF Trace, GoBPF, and Frieda. I would say Delve is really the place that you want to start if you're interested in doing this type of work because it's the one that supports Go the most. So there's just a quick table of like all the different things you might want to do and their support. Again, like I mentioned, Delve supports pretty much everything. Where Delve kind of falls over is its use of Ptrace means that it's not suitable for performance measurements and high frequency events. So under those situations, you want to reach for one of these other tools, and they have different trade-offs. So yeah, just to conclude, static instrumentation is great, but it doesn't provide the total coverage of your programs. Dynamic instrumentation allows you to observe every aspect of your program as it's running without it knowing that you're doing that, which is really powerful. There is no free lunch, so you're always going to pay a performance penalty for any instrumentation that you add. Delve is really awesome and has a great API. You know, previous to discovering this API, I was sending commands to Delve via standard in and reading from its standard out, and it's very painful. So if you're going to automate Delve, I definitely recommend using the API. And finally, BPF Trace, GoBPF, and Frieda are really excellent tools whose support for Go is continually improving. So yeah, with these tools, we can achieve new levels of understanding about how our programs are running, and I hope you find them as useful as I do. Thanks. So yeah, I welcome any questions you all have. Just really quick, these are kind of some references. Watt.io is my website. If you hit watt.io/source, you can get all the source code for the presentation. And these are the 5 repos of the tools that I demonstrated today.
Hi.
Hi.
Great talk.
Thanks.
Is there any way for any process to protect itself against this kind of access?
Yeah, so for Ptrace, you need to have the either syscap admin or syscap Ptrace on Linux to be able to do that type of operation, or be root. If you're not a child process, so debuggers sometimes will spin up a child process, and that allows it to Ptrace without having that capability. So if you're tracing a process that's not a descendant of the debugger, then you need to have those capabilities. So without those capabilities, the process is kind of protected from being instrumented. The other techniques I went over, so with BPF Trace, there's really BPF and uprobes really, if you have the privileges to inject the BPF program into the kernel, there's nothing the process can do to prevent that. With Frieda, yeah, I think you need root in order to instrument with Frieda. So.
Hello, thank you for the talk. One question about, have you run this dynamic debugging and stuff in production or in staging environments, and how does it work in there?
Yeah, so I've done several of these types of instrumentation tools, like one-off tools to debug issues in production. That's what kind of drove out my use of this technology. And really, it's kind of like the tool that I reach for when everything else fails, when static instrumentation is not pointing you in the right direction, you're not collecting the right information, when there's a long feedback cycles and pushing changes to static instrumentation, that's when I attach to the production systems and just instrument them directly. It obviously depends on like your infrastructure and like whether that's allowed or not, but if you can do that, you can do it very safely using these techniques.
Okay, thank you. Oh, yep. One more question, if it's possible.
Yeah.
Do you have a go-to approach to do it in Dockerized or container environments? Or
yeah.
something
So
like that?
the environments that I was referring to previously are Kubernetes based, and there's actually a really great tool called kubectl trace, I would recommend checking out. I don't have internet on here, but if you just Google for kubectl trace, I think it's in IOVisor, and it kind of allows you to schedule these BPF trace jobs across your clusters so that you can instrument things. Yeah.
Perfect. Thank you very much.
Any other questions? No one? Okay, thanks, Jason.
Yeah, thank you.